All right, let's take a look at question number 10. So question number 10 uh, gives us it wants us to find, or it gives us the current through the 0.5 capacitor shown. At time 0, the voltage is 0. V of C 0 is 0 volts. And they want us to find the voltage across the capacitor and the stored energy. So we know time is going to be equal to 3 milliseconds. Okay? So let's look at our circuit because this gives us A and B. It wants us to find voltage and energy. Notice here, there's only this capacitor here. There's only this capacitor. And this graph gives us current and time. And you might be asking, well, okay, well, it involves time, so it's a transient problem, and you would be 100% correct. However, if you go and write out the charging-discharging equation, you'll notice that tau is going to be equal to RC. And nowhere in this problem do they say anything about tau. They don't say, resistor is equal to this, or they don't say time constant is this. They don't mention time constant at all. So there's no way for you to actually go and find a tau. So you can't do the charging and discharging equation. So instead, what you need to do is jump over to your handy-dandy formula sheet and take a look at your left-hand side of the equations. These are going to be the capacitors. And we'll notice here that we have a voltage equation, and then we have an energy equation. So energy is denoted by W here. So let's jump back to our problem. I'm going to write these real quick for us over here on the side. So V of C time is 1 over capacitance value, T1, T2, I of C, point in time, dt plus V of C at time 1. And real quick, time 1 here is going to be equal to 0. So with that in mind, let's look at what we have. We know VC initial is going to be equal to 0, so we can go and simplify that out. And the other equation, let me write that out while I got it here. It's equal to 1/2 CV squared. That's the energy equation. But now, what we can do is we can use this equation and the knowledge from this A and B, and we can integrate to find these values. So you'll notice here that this contains our capacitance value, and we're going to only 3 milliseconds. So we have this bit, and that bit. So we're only concerned with right there. So if we go and write out our integral equation, so V of C, 3 milliseconds, 1 over C. Notice it's not a continuous function, so we're going to have to do a piecewise on it. So because it has this weird break right here where it has a sudden drop vertically down to 0, we've got to do 2 pieces. So 0 to 2 milliseconds, our value is 20 milliamps. And we'll integrate that with respect to time. Plus 2 to 3 milliseconds, our value is 0. Therefore, dt. All right. So if we go and integrate this, what will end up happening is we know this value here is just going to drop out and go to 0. But then over here, we'll have 1 over our capacitance value, which was 0.5 microfarads. If we integrate here, we'll have 20 milliamps. Integrate 20 milliamps, we'll have T. So 2 milliseconds to 0 milliseconds. So if we go and plug and chug, milliamps there, milliseconds there, minus 0 milliseconds here, all over 0.5 microfarads. And remember, we want to keep all this in base units. So 20 times 10 to the negative third amps, 2 times 10 to the negative third seconds, over 0.5 times 10 to the negative 6 farads. And this will come out to be and this will give us 80 volts. So there we go. So that is V of C at 3 milliseconds. Just looking at what's under, it's area under the curve, really. So just what's right there, that has no area. There's no rise to it. So, yeah. Yeah. That's part 1. Okay, and the reason why we did this is because we're going to need it for the voltage value there. So if we go right, make a C at 3 milliseconds, 1/2 CV squared, which will be equal to 1/2. And we're going to keep it in base units. So 0.5 times 10 negative 6 farads. Voltage is going to be 80 volts. Square that. We're going to get 0.0016 joules, which is equal to 1.6 microjoules energy at 3 seconds. And looking at our values, we are getting the same thing.